Hello, this time I want to introduce a very useful technique for estimating the amplitude response of circuits, the Bode approximation. In order to use this technique, we first have to know where all the zeros and the poles are and what the gain of the circuit is at one frequency. So we still have to do all the circuit analysis, and we still have to do all the job of factorizing those polynomials to work out their roots. But having done that, we can use the Bodhi approximation to very quickly sketch the approximate frequency response of the network. It's based on this equation, the equation that we get when we take the amplitude response and we express it in terms of dBs. And we see that the total amplitude response is the sum of all of these terms, a term due to the gain at low frequencies of the network, terms due to the zeros at 0 Hz, and terms due to the zeros and the poles at other frequencies. And we've seen what the effect on the amplitude response is of each of these terms individually. A quick reminder, this term here just provides an offset, moves the whole graph up or down. The effect of a zero at 0 Hz is to introduce a rise of 20 dBs per decade in the amplitude response. And that's at all frequencies. The effect of a zero not at 0 Hz is to introduce a rise in the amplitude response of 20 dBs per decade at high frequencies, a long way above the break frequency, and it has no effect at all at low frequencies, a long way below the break frequency. And the break frequency is just the magnitude of the zero. I've expressed things in hertz here rather than radians per second. Likewise, the effect of a pole is to have no effect whatsoever at low frequencies, a long way below the break frequency of the pole, but to reduce the gain by 20 dBs per decade, a long way above the break frequency. And the break frequency of the pole is just the modulus of the pole frequency. Once again, I've expressed things in hertz here. F is just omega over 2 pi. F of P is the pole in hertz. It's just P divided by 2 pi. The 2 pi's cancel. So, in both cases, with a zero, at lower frequencies, the zero has no effect. At high frequencies, it produces an increase of 20 dBs per decade, and around about the break frequency, it introduces a curvy bit. The pole does a similar thing. Low frequencies, no effect at all. High frequencies, above the break frequency, it causes a decrease in the amplitude response of minus 20 dBs per decade of frequency. And around about the break frequency of the pole, it introduces a curvy bit in the response curve. And we've seen that we can express the total amplitude response in dBs as the sum of all of these terms due to the zeros and the poles and the gain. We're now ready to introduce the Bode approximation. The Bode approximation is just to note that the total amplitude response is the sum of all of these individual contributions, and that at frequencies below the break frequencies of the poles and the zeros, it's very easy to determine what that contribution is. It's only around those curvy bits at the break frequencies of the poles and zeros that things get a little bit complicated. Bode just proposed that we ignore that complication. And we just assume that the low frequency approximation is accurate up to the break frequency, and the high frequency approximation is accurate above the break frequency. In other words, for a pole, we would approximate its effect as a straight line up to the break frequency of the pole, which is the modulus of the pole, and it just goes down at 20 dBs per decade afterwards. So there is a corner at the modulus of the pole. And that's why this frequency is sometimes called the corner frequency, as well as the break frequency. And the effect of a zero is similar, except that it bends up at 20 dBs per decade at the break or corner frequency associated with that zero. Should always label axes. Gain, dB, log of frequency. And then all you have to do is add up all of the contributions. We'll do some examples of this in the next video.